Okay, so, chemists, where we left off. We were talking about how complex ions can increase the solubility of poorly soluble substances. So if we can complex them, we can increase the solubility. So here's where we are. Complex ion formation can have a major effect on solubility. So we looked at how silver chloride is much more soluble in ammonia solutions than in pure water. Well, since NH3 will form a complex ion, it removes the Ag plus from solution. So if you think about this in terms of that dude, if Ag plus goes down, if Ag plus goes down, which way does this shift the equilibrium? To the right to make more ions, which increases the solubility. So as I remove Ag plus, I push my equilibrium to the right, and I get more soluble. And that's what it says. Okay. Here are, oops, I have this in different order. Hold on one second, guys. Oh, so this is what we talked about before. Just how we can use, why does his name keep coming up again and again? Use the principle to make qualitative predictions and couple the reactions to make quantitative predictions. I don't know. Yeah, the question was, what is his first name? Maybe I should like learn or come up. What is it? Le. His first name is Le. I could call it like the French principle, or LC's principle. Because I can't say. I will do my best. So, it's just because Mr. Hamill just gives me such crap about it all the time. Now it's a thing. So, all right. I'll learn it. I'm gonna remember when it was really hard. I'm gonna remember when it was really hard, and then think back. All right. So, here are just some examples of complex ion formation. So aluminum. Remember how aluminum can get the 6 water molecules around it and act as an acid? Well, aluminum can also get 4 hydroxide ions around it to become a complex ion. Copper and ammonia. So CuNH3,4. Silver. This is one, if we end up doing, the AgS2032 is one that if we end up doing the 12 solutions lab at the end of the year, this is a reaction that you'll see. And then one with cobalt as well. So if you look at the KFs, we have 10 to the 33rd. So in terms of thermodynamic favorability, what does that mean? Very, very favorable, right? So these complex ions form. Again, if we think about the central atom, Al3+, very small, high amount of positive charge, copper, silver, and cobalt are transition metals. So they can form nice, stable complex ions. Okay, we have a weird example. It turns out that aluminum hydroxide is more soluble in concentrated solutions of a strong base like NaOH. Why does this not make sense? Well, what is normally the dissociation reaction for this? If I dissolve this in water, what do I get? Whoever's birthday is closest to mine, September 18. 4? Anybody else? No one else in September? All right, Johanna, what is the equation? Well, let's do the AlOH3. Yeah. Right. So if we would think that we put this into a concentrated base, our thoughts would be that still no Griffin. I saw Griffin. The OH minus goes up, and it should the OH minus goes up, and it should push back and actually decrease the solubility. Well, it doesn't happen. So what actually happens is we have this same first reaction, but then we have aluminum reacting with 4 OH minuses and making that complex ion. And remember, this K is 1.1 times 10 to the 33rd. Well, what's our KSP for aluminum hydroxide? Somebody who has the blue sheet out. Aluminum hydroxide. Two times 10 to the negative 32. Thanks, Halen. Equals 2 times 10 to the negative 32. Wicked unfavorable, right? But when I couple these two reactions and I get the overall of AlOH3 plus OH minus makes AlOH4. Well, now my K equals, 22. We are now thermodynamically favorable. So I took a reaction that was hugely unfavorable, coupled it with a favorable reaction, and overall now aluminum hydroxide will dissolve in a concentrated base. So it goes against our intuition. Yep. Excellent question. So the question was, why do coupled reactions happen? If the first reaction is so unfavorable, then how can that second one even take place? So what happens is, even though this is extremely unfavorable, any amount of, this first reaction is extremely unfavorable. Any amount of aluminum that gets produced immediately reacts with the OH. So any small amount will go away, and then it constantly shifts right. Yeah, so as the Al gets used up, it shifts right to make more, and then that Al gets used up, and that Al gets used up, and it just keeps shifting and shifting and shifting. Yep. Mm-hmm. Okay. So, for this, what does that mean about my sign for delta G? Remember, favorable delta G is less than 0. Good things to remember for your cumulative and our end of the year stuff. Okay, so now let's figure out what is the molar solubility of AlOH3 in 2 molar NaOH and compare it to the solubility in pure water. So I want you guys, since we're almost done, I want you guys to do this one. So try it. Complex ion, weird example, calculate the molar solubility of aluminum hydroxide in 2 molar NaOH. So on a side note, Thomas, I'm happy. Yeah, but cool. All right, chemists, let's check to see where we are. So this is what you should have set up. Now, what's my initial concentration of OH minus? 2, and I have none of the complex ion. So I subtract x, add x, and at equilibrium, I have 2 minus x and x. Now, the trick here is your K value. The K value is the one from coupling those two reactions. So the slide before, when I showed you the first reaction and the second reaction and combine them, that's how we get the K. So I set 22 equal to x over 2 minus x, and I get x equal to 1.91 molar. Now, what is the concentration of aluminum hydroxide in pure water? What's the molar solubility? We go back and look. I think we did it before. Aluminum hydroxide in water. Did we not do it? Oh, you know what? We didn't do it. All right. So, good. That's why I put that other slide there. So we have all right. So again, 0, 0, 0. All right. Trick here. X, 3x. Because I have the 3 OHs. And so I have x and 3x. And my KSP expression is Al3 plus times OH minus cubed. So 2 times 10 to the minus 32nd equals x times 3x cubed equals 27x to the 4th. And if you solve for x, you get 5.22 times 10 to the minus 9th is your molar solubility in pure water. So there's almost zero solubility in pure water. But if you take aluminum hydroxide and add it to a concentrated base, it becomes very soluble. This is not a normal process. Don't assume this happens unless I give you a complex ion. Okay? If I give you the complex ion, then you can couple the reactions. But in general, if you put a base into a basic solution, you're going to be less soluble because you have the common ion. Okay, summary of solubility. Molar solubility. Number of moles of a compound that can be dissolved per liter. Straightforward. Common ion effect. This is what I was just reminding you guys about. A salt is less soluble in a solution containing a common ion. So what you'll see a lot is something like putting silver chloride into salt water. NaCl already has the Cl minus ion dissolved, so AgCl is less soluble if there's already chloride ions there. pH effects. Basic salts are more soluble in acidic solutions, except for the one we just saw. And complex ion formation. A salt is more soluble if one of its ions can form a complex ion. Yes? Oh, okay. Not a question. So now we have so many Ks. Ka. What is my equation that governs Ka? It's like general, generic dissociation reaction. So Ha, what does this become? H plus plus A minus. My Ka equals H plus times A minus all over Ha. I put it in the back. In a box. Because the box went away. And when I tried to put it back, the box wasn't there. Mr. Hamill interrupting me like always. Okay. So, KB. B plus H2O. It should be right in that top box. All right. Makes BH plus OH minus. And what's the KB for this? Just shout it out. So remember, it's always products over reactants, but you have to know the correct chemical equation. KW. This one, if you haven't started problem set 19 yet, I mean, you have 4 days, and I'm not going to be here for one of them, so you have lots of time. I wouldn't recommend waiting until Sunday night, though, because it's long. This one comes up a lot in problem set 19, where we have H2O equals H plus OH minus, and KW equals 1 times 10 to the minus 14th equals the concentration of H plus times the concentration of OH minus. You'll find that you'll use this. Actually, what you'll use a lot in problem set 19 is the inverse of this, which is 1 over KW. You'll see when you get there. So we also now have KSP, which is take any ionic compound, MX, metal, and X is your nonmetal. You get M plus X minus. All right. There's actually one we didn't show up here that I just touched on at the end of, we talked about a little bit today, which is KF. That one's a lot less common, which is the K of formation, and those tend to be big numbers. All right. Objectives. Whose birthday is closest to today? Whose birthday is close to today? March 6th? Can anybody beat March 6th? All right. Ian. Read the first learning objective, please.
The student can use the Chatelier principle to make qualitative predictions for systems in which coupled reactions that share common intermediate drive formation of a product. Yeah.
Okay. So that was Ian's very enthusiastic reading of AP Learning Objective 516. A round of applause for Ian. So basically what this one means is you can look at a system that has coupled reactions and predict which way the reaction will move based on those coupled reactions. Okay, 517. Who is the youngest person in the classroom? Who is youngest? Who's still is anybody still 15? 16. We have 2. So whose birthday's next? When's yours? May 6th and May 4th? Yeah, that's right.
No, wait, which one do I have to read?
The next one, 517.
The student can make quantitative predictions for systems involving coupled reactions that share a common intermediate based on equilibrium constant for the combined reaction.
All right, thank you very much, Johanna. All right, so that is like when you coupled the reactions and have the 2 K values. So like the ones we're doing at the end, where you have to multiply the K values together to get your overall K for the coupled reaction. Next one, what do you think? Where do you think I'm going with this one? Oldest, who is 18? All right, whose birthday was a long time ago and is 18? September? Last one, Thomas. Who you have on the page?
Student can predict the solubility of a salt or rank the solubility of salts given the relevant KSP values.
Right, so this one's like when we ask you to rank the strength of an acid or base, giving you Kas. The only trick to this, you can't just look at the KSP. you have to look at the equation that governs the KSP. So sometimes you can have, like if it's NaCl, well, that's a bad example. If it's silver chloride, it's Ag times Cl minus, so x squared equals KSP. But that one for aluminum hydroxide, we had 27x to the fourth equals the number. So you have to look at the equation that governs the KSP before you immediately jump to one being more soluble than the other. All right, 3 more. Give me a suggestion for how I should determine. Carter had a joke, and I'm not sure I want to. If it's what was it, Carter? What was it that you said? Oh, who has the lowest grade in the class is not a good thing to choose. Who has the highest? Also probably not fair to put that person on the spot. And I actually don't know who it is. Hey, Mr. Hamill, do you have a second? Can you read Learning Objective 6.22? No, he refused. This is our last. We're just sharing out. I feel dissed. I just gave Mr. Hamill a proposal and he turned me down. All right. No, because then the suggestion was I read it, but I read it in a voice. And in all honesty, I'm worried it would come off as racist. Because if I use a voice that's like, all my voices sound the same, and I don't want it to be misconstrued as any sort of. Yeah, see, that could come off not okay. All right, I'll read them quickly, and then you know what? As a class, we'll read the last one together. Okay, so 6.22, the student can interpret data regarding solubility of salts to determine or rank the relevant KSP values. That's like something you would do experimentally. So a student can interpret data regarding the relative solubility of salts in terms of factors that influence it. So this would be when you're adding a salt to something that has an ion, common ion, or you're adding something that is affected by acids or bases. All right, 6.24. All of us go. All right, good job, team. Thank you guys for listening.